Hi everyone, our topic for this report is hybrid photon-plasmonic nanowire lasers. And this is a paper from Nanoletters published in 2013. And here is our presentation agenda. First, we will introduce the background of nanowire lasers. Then the methodology and experiment this paper demonstrated. After that, we will show you the results and conclusion of this new structure of hybrid nanowire laser. Okay, so let's begin with the introduction. As coherent sources that can provide optical frequency radiation well below the classical diffraction limit in one or more dimensions, nanoscale plasmonic lasers have been attracting more and more attentions. So for starter, let me briefly introduce what is plasmonic lasers. Plasmonic laser, or so-called spacer, which stands for surface plasmon amplification by stimulated emission of radiation, and is a type of laser which aims to confine light at a sub-wavelength scale far below the diffraction limit, and by storing some of the light energy in electron oscillations called surface plasmon polaritons. And this phenomenon was first discovered in 2003. A little bit different from the conventional lasers. A typical configuration of plasmonic nanolaser includes a process of energy transfer to convert photons into surface plasmons. So in this type of laser, the excitant is not photons anymore, but surface plasmon polariton. And surface plasmons are collective oscillation of free electrons on metal surface under the action of external electromagnetic fields. However, all the plasmonic lasers reported so far operated in hybrid photon-plasmon modes in the direction transverses to the propagation direction. This makes it impossible to separate a pure plasmon cavity mode from photonic component. So consequently, only the far-field photonic component can be measured and utilized directly. And this is a drawback because for practical applications, direct access to a plasmon cavity mode is an important approach to provide nanoscaled confined fields for light-matter interaction. Moreover, separated plasmon cavity can be modulated with ultra-high rates. Second, let's talk about methodology. For plasmonic waveguiding, silver nanowires are of particular interest owing to their low dissipative loss. Also, the polaritonic resonances of silver nanowires match the gain spectral range of some high-gain semiconductor nanowires. In this case, cadmium selenide nanowires. We will mention the benefit of this feature later, but first let's talk about the X-shaped structure proposed in this paper. As you can see in this picture, a silver nanowire is side-coupled to an ultra-long cadmium selenide nanowire. This is the silver, and this is cadmium selenide nanowire. The coupling coupling point is located close to the left end of the cadmium selenide nanowire, dividing the nanowire into two segments. The shorter one to the left serves as a gain medium under optical pump, and the longer one to the right, that is outside the pump bin and highly absorptive around the emission band of the cadmium selenide, serve as a distributed absorber to eliminate reflection from the right side of the nanowire. As shown in this figure, the PL photoluminescence from cadmium selenide bandage is wave-guided along the nanowire until reaching the joint area, which is here, where the photon modes of the cadmium selenide nanowires are coupled and converted into plasmon modes of the silver nanowire. The reflection of plasmon modes at the right end of the silver nanowire and photon modes at the end of the cadmium nanowire alternately recirculates photon and plasmon modes for lasing oscillation in this longitudinal hybrid cavity. This is the key difference between plasmonic nanolasers reported before and the one shown here, the way plasmonic and photonic components are coupled. In the papers reported before, those components are coupled in a transverse direction, but in this one, the components are hybridized along the longitudinal direction and thus spatially separated. Above the threshold, the bidirectional propagation constantly converts energy between the photonic and plasmonic components, providing spatially separated photonic far field output from the end of cadmium selenide nanowire, while highly localized coherent plasmon modes from the end of silver nanowire simultaneously. Generally, when the cadmium selenide nanowire is excited, a large fraction of PL, photoluminescence, is channeled into guided modes and reflected at the end faces of both cadmium selenide and silver nanowires, which may form four resonant cavities, one end phase 1 to end phase 2, and phase 1 to end phase 3, end phase 4 to end phase 2, and finally end phase 4 to end phase 3, as shown in this figure. Here, the pumping light is focused on the left segment of the cadmium selenide nanowire, while the right segment outside the focusing area is served as a non-reflective absorber here. Thus, only one active cavity that consists of the left segment of the cadmium selenide nanowire and the right segment of the silver nanowire works. Okay, now let's talk about how the experiment was done. Figure A is the scanning electron microscopy image, SEM, of one end of a 390 nanometer diameter cadmium selenide nanowire. And figure C here is the SEM of one end of a 100 nanometer diameter silver nanowire. Figure B is the spectrum of the cadmium selenide nanowire, and figure D is the spectrum of the silver nanowire. As you can see, the PL of the cadmium 39 nanowire is centered around 722 nanometer, with a full width at half maximum of 18 nanometers. 18 nanometer FWHM indicates that the cadmium 39 nanowire has a tight confinement. The gain of the cadmium 39 nanowire and the plasmonic resonance of the silver nanowire are well matched in spectra, making it possible to compensate the ohmic loss of the metal for lasing action in a hybrid photon-plasmonic nanowire cavity. Okay, in this page, we can see the coupled structure of the hybrid cavity from the SEM image. Using fiber probes for micro manipulation, the hybrid cavity is assembled from a 100 nanometer diameter, 11 micrometer long silver nanowire, and this one here is a 390 nanometer diameter, 470 micrometer long cadmium 39 nanowire. The left segment of the cadmium 39 nanowire and the right segment of the silver nanowire are 28.6 and 3.7 micrometer in length, respectively. The overlap length of the two segments here is about 1.1 micrometer, long enough for efficient photon-plasmon conversion. And let's see this figure. By exciting the cadmium 39 nanowire at the right side of the coupling area with a 532 nanometer wavelength light, we observe evident output from the silver nanowire here and determined a photon-to-plasmon coupling efficiency of 20%.
And now, let's move on to the session of the results. And this is the optical microscope image. Under excitation, strong luminous spots are observed at both ends of the hybrid cavity with clear interference rings, like this one and this one. And that indicates strong spatial coherence of the light emitted. And we can see the output spot of the silver nanowire, this one, is much smaller than that of the cadmium selenide nanowire, like this one, and which indicates much tighter confinement of the SPP radiation. This is the lasing spectrum. Figure B is for silver, and C for cadmium selenide nanowire. The bump influence is from 27 to 97 microjoule per centimeter square. And now, let's look at the red line. It shows that the dominant lasing peak is centered around 723 nanometer, and the line width of that lasing peak is 0.38 nanometer, which indicates the high quality of the cavity. And we can observe that the cadmium selenide nanowire shows more clear PL background. Compare the two lasing spectrums. The cadmium selenide shows a small peak around 745 nanometer here, coinciding with the peak single cadmium selenide nanowire dynamics, which indicates the coexistence of both hybrid cavity and single nanowire cavity mode. On the contrary, there is no peak around 745 nanometer in silver nanowire, and that indicates the output is purely from hybrid cavity. And then we focus on the emission output, with the bump influence increasing from 27 to 97 microjoule per centimeter square. The emission output experiences a three-stage transition. that is, spontaneous emission, amplified spontaneous, and full lasing oscillation. First, spontaneous emission. The gain from the cadmium selenide nanowire is much lower than the loss of the silver nanowire. And second is amplified spontaneous, the cavity gain approaching the loss. And the last is full lasing oscillation. The output exhibits a linear dependence on the bump intensity. And now let's focus on the upper left figure. It is log scale of the larger figure. We can observe the three stages more clearly here. And with the increasing bump intensity, both silver and cadmium selenide show synchronous evolution from spontaneous emission to lasing oscillation with almost the same threshold, about 60 microjoule per centimeter square. As we can see, the threshold of the single 470 micrometer long cadmium selenide nanowire is about 90 microjoule per centimeter square here, and that is much higher than 60 microjoule per centimeter square of the hybrid cavity, like this, which indicates the lasing emission with pumping intensity below 90 microjoule per centimeter square coming solely from the hybrid photon-plasmonic cavity. The last is the conclusion section. First, a clear case of hybrid photon-plasmonic nanolaser with simultaneous and spatially separated photonic and plasmonic outputs are established. And second, silver nanowire can offer special merits such as ultra-tight confined optical fields and ultra-fast modulation in dielectric constants. Third, the highly localized and spatially separated plasma modes can be efficiently delivered to an application point or to other photon emitters, such as quantum dots, and served a localized excitation source for quantum information applications. And the last, since the spot size of a pure plasma mode is solely determined by the diameter of the silver nanowire, it is possible to achieve a plasmonic source with a size far below the diffraction limits.